provide just a moment. And
Okay.
we are live. So B-Sides Idaho, thank you very much for coming to watch. This is Rita Foster presenting Binary, Malware, or Essential Executable. Rita, take it away.
Thank you. Thanks, B-Sides Idaho. I really was upset when I heard that B-Sides Idaho Falls was not going to be able to go. It's one of my favorite events to attend. So I'm really glad that the Boise folks have been able to step in and do this. Again, my name's Rita Foster. I'm from the Idaho National Lab. My focus is mainly on the more very edge research areas that have to do with cybersecurity. I've worked there for over 30 years. The vast majority of my work has been in control systems. And then I saw that we were doing cybersecurity of control systems about 15 years ago, and that's when I switched over, mainly focused on the electric grid. So today I want to go over a couple of tools that we created. Some of them are available to all to help promote new directions in research and new capabilities. So the title is Binary Malware or Essential Executables, and we'll go over some machine learning binary analysis capabilities that we've created, mainly focusing on that test corpora for machine learning. So this project was funded by the Department of Energy, their cybersecurity for energy delivery systems area. It was a competitive research call. I wrote the proposal and we got it. I listened to our leaders and cybersecurity researchers to put this together. So that's a shout out to there. On the corner, you're seeing all these funky little dots. That's some of our visualization capabilities we have, but we'll get to that here in a little bit. But firmware indicator translation or fit, our whole goal was to look at firmware. The electric grid has tons of devices, whether they're relays or network gear or a switch that has a lot of code inside of them, and you really don't know what's inside of those. There's a lot of ubiquitous libraries. Some of those libraries are very old versions, so they have a lot of known vulnerabilities. So our whole goal was to find these ubiquitous libraries with known vulnerabilities so that we have a better understanding of how to defend these most critical systems. By doing that, what we have done is we focused on binaries. Binaries are the ground truth. Things happen, things change in these systems. They have a very long lifespan. And if I got the source code from one vendor versus another vendor, that's only going to tell me probably about 60% of the story. As we know as cybersecurity researchers, most of the vulnerabilities happen in the implementations. So we created an initial triage tool called WiiBin, or What Is It Binary? Because a lot of times as a cybersecurity defender, you're trying to defend a bunch of file systems, and then all of a sudden you get something that doesn't seem to make a lot of sense because there's only one or two unknown binaries, and you're really trying to figure out what it is. WiiBin will help you do that initial triage. Our big application that we create is @DISCO, otherwise known as Annotated Translated Disassembled Code. We took the reverse engineering at scale concepts, the methods that were developed with internal research at Idaho National Lab, and we implemented them in one concept using all open source technologies. So that has the potential of being sharing. We put this in a graph database, which allows for amazing visualization. We call our visualization tools DISCOverFlow because it uses @DISCO technologies to do that. And then we're moving forward with a lot of these technologies with future research projects as well. So why did we do FIT? Here's an example of what embedded systems look like. You have CPUs with certain instruction sets. You have microcode that goes and tries to enhance those instruction sets. You have a basic input-output system on your devices. You have real-time embedded systems. You have tons of interfaces with everything else, whether it's memory or storage or communications. And then you have the original equipment manufacturer who puts their secret sauce on top. Then you have third-party integrators who, as they're going through the life of the project, they're doing the initial install and maintenance. You have the asset owners who also make changes to code and regular old maintenance as you go along. So with all these fingers in the pot, all these different sources of code, this is why binary is the ground truth. This is also why our adversaries, as we call it, race to the bottom. They are targeting embedded systems because they know we do not have decent monitoring and detection capabilities on these embedded systems. So when this project started 3 years ago, I went out and I just kind of mapped what we believe our layers of firmware are back to what does it look like for the different malware campaigns that we have seen. We've seen Spectre, we've seen Meltdown doing that speculative execution. That's between that microcode and the instruction set. But unfortunately, when the different operating systems fix that, they're fixing it at a higher level. So you still have that underlying problem. And we've seen that time and time again as we're going through. Other big malware things was with the Lenovo laptops. That was almost over a decade ago. The US Congress had to go out and buy a whole bunch of new laptops because of the known backdoors from that manufacturer. Trisis was original equipment manufacturer targeted malware. It affected some very large refinery in the Middle East, and we'll look more into the Trisis code here in a little bit. But the other reason we did fit is because at the Idaho National Lab, we have a lot of experience with reverse engineering. We have over 300 people that are focused on the cybersecurity of control systems, not IT, but critical infrastructure and control systems. Not all of them are reverse engineers. Only a very few people are actually sitting there reverse engineering, whether it's malware or other code, try to figuring out where the potential vulnerabilities are or how to detect malware. It's a very difficult tool set. It's a very difficult skill set to find and obtain. We are the lead lab for nuclear, so we kind of call that problem set unattainium, because there's no way you're going to get an army of reverse engineers to go and reverse engineer all your code and understand everything so you can have better protections. Here's an example on this slide. This is exactly the same code. This is reverse engineered in Binary Ninja. It would take a researcher a very long time looking at these two different pieces of code to understand they're exactly the same, because they definitely do not look the same. The only thing that's different is the optimization flag on the compile. That's it. So this is why we developed these tools. Our first product the three products that are coming out of the FIT project is WiiBin, as I mentioned before. That's for initial forensics. It's a triage tool. You have to understand what's happening with that binary before you load it to any reverse engineering concept. So we have things such as Indianist architecture and where the potential operation codes are so you can start reverse engineering or doing your other areas. It uses binwalk, and we're getting some really good results. A lot of times with malware or other binaries, you don't get the full file. So we're getting some really good results with only 30% of that file. We'll go into that a little bit more. The Annotated Translated Disassembled Code, or at DISCO, that is our test corpora. That is where we are using those reverse engineering at scale methods. We are translating the code. We're using Anger as our open source reverse engineering tool. We're using Vex as our high level language. We're putting that into an OrientDB, a graph database. And we can also do many control flow graphs, which you'll see here in a bit. And it's a really great research area because it creates the set that you can ask many questions for later. And that's exactly where we need to be at the Idaho National Lab, so we're doing some advanced research and enabling others to do research. And then finally, DISCOverFlow. I like to say DISCOverFlow, which they don't like to say. But DISCOverFlow allows different 3D images, control flow graphs, and execution flow. All these products work on static binaries. So some more on WiiBin. WiiBin has a little small user interface. It's going to identify the Indianist, whether you have your big most significant or your little least significant byte first, so you can start doing other processing. It'll tell you what architecture that this has been compiled for. There's a lot of cross-compile technologies. There's a lot of different platforms out there. You really need to understand that because things load differently, whether it's the Indianist or that architecture that's been compiled for. And then it'll give you the concept of where that data offset is. So histograms of binary code is something that we have looked at and used quite a bit. And then you can do an entropy analysis on those histograms using binwalk. Over here, you're seeing an entropy analysis, and the things that are highlighted in red on the bottom, those are pretty much nulls in that binary code. If you sit there and you're poking through those, it's going to take you a very long time. On the top, these are probably things that are compressed or encrypted. Again, if you're sitting there trying to reverse engineer this, it's a lot of waste as well. But you can determine a lot by these different peaks and valleys that are in the middle. And that's what binwalk is taking advantage of. And then once you have that, you can run it through some very, very well-known supervised machine learning that's going to do some clustering, that's going to do some similarity checks, and you can identify what is happening with that piece of binary. Here you're seeing an example of about 8 different machine learning techniques: random forests, simple vector machines, k-nearest neighbors, and you're seeing the percentage of the file that we were able to feed into that system, and the green indicates that we're pretty confident it has identified it correctly. We're kind of using just the number of 80% and above of accuracy as being good. So with 80% of accuracy, you're seeing the identification of this architecture being pretty much MIPS. So the overview is you start off with your binaries, you get a test set, you get a training set, you train your byte histograms, you get some sub-byte histograms, you put it through some machine learning. We're using TensorFlow, we're using scikit-learn, and we're using some very basic, open and available machine learning techniques. You get your results, and then you can go forward. Brian Beckman is the one who is the brainchild for this little application. He used the machine learning that Jed Hale developed earlier and created this application. There's some settings you can do for understanding your entropy span, whether it's 80% and 10%, or whether you want to change that, what type of block size you want to go through. The other thing I want to kind of point out here is somebody here is named Karina, excuse me. Karina was one of my interns last year and the year before. This year, she's a first-year freshman at University of Idaho. Last year, she was a high school student. So we're really committed to make sure that we are using a lot of interns. We're using a lot of people from Idaho in order to promote these technologies. This result that you're seeing on the screen was one of the cybersecurity challenge. I had 16 different interns doing the cybersecurity challenge, only one high schooler, Karina. And I had to challenge her. She kept using everything in IdaPro, and I said, no, you have to use our tools. That's the whole point. She's kind of a whiz at IdaPro. So that was an interesting concept for her. But she went through all the challenges faster than anybody. Really, really excited to see what happens to her in the future. So now we're going to change and talk about the big application that we created at DISCO. It does still use supervised machine learning. There's potential to use other type of machine learning, but that's what it's used for now. Again, it starts with binary code. It gets disassembled with Anger with the @disco application, and then it gets loaded into a graph database with the VEX commands. After it gets loaded, then you can start seeing all these control flows and how this code is actually working. You're looking at a library. That library consists of different functions. Those functions consist of different blocks and different instructions. So what happens is that in machine learning world, the VEX language is your feature matrix. The connections between the different parts of code, that's your adjacency matrix. So more examples on VEX. Binary looks like this. If you reverse engineer it for a specific platform, it's going to look like this. There's an example of that piece of binary if it was going to be for an ARM processor. But then we can translate it into VEX and get things that look like commands. The other benefit of @disco is that it protects people's intellectual property. People get extremely nervous when you're reverse engineering. They don't want you stealing their IP. But you can't get from VEX all the way back up to that binary. That requires, VEX is not executable. It requires a heck of a lot of work. So it just is not going to happen. @disco was designed to be architecture independent. We don't care if it's an ARM. We don't care if it's a PowerPC. We don't care if it's x86. Compiler independent. We have tried this out on some interpreters that have been executed. Optimization flags and coding language. Another example of the @disco capability, we believe it has use cases for, of course, reverse engineering. It takes it from, could be weeks to a year effort to hours to a week. Huge efficiencies there. Supply chain, you can see where things have changed in the code, and software quality assurance. We're starting a new project right now that's going to deal with more software quality assurance of code using these processes. Jed Hale and Sage Havens are the ones who created the @DISCO applications, and there's an IEEE paper for that as well. And here is that trilog running through VEX. It creates this feature matrix. On top here, you're seeing the VEX commands, and you're seeing the counts of those. Here's an example of the Orient database where you can go to those different libraries and actually look at the VEX commands in view. And then finally, we have a lot of visualization capabilities. So DISCOverFlow allows us to do 3D imaging of the code. It allows us to drill down in some of these 3D images to get all the way back to the Orient database to see the commands. And it also allows us to create control flow graphs and execution flow graphs, which can also drill back down to the OrientDB database to look at the VEX code. So really fine capabilities in being able to go back and forth within the code. And it's there. You don't have to reverse engineer it or refigure out where you are in that reverse engineering debug cycle. So here's a video. I hope it's going to turn out with everybody's internet connections. But you're seeing a center piece of code there and then the softball piece of code that's separated. This is Trisis. This is the malware that infected a safety instrumented system in the Middle East. The very middle is trilog.exec. The relationships have values that has branch true, branch false. It has a feature. There's about 8 different relationships in there. The edges have value. The blue is the library. The light blue is the blocks. The greenish yellow are the features or the functions, excuse me. And you can drill down as fast as you want and figure out what's happening. This model right here is called a Springs 3D model. So you can grab one of the nodes and one of the edges and kind of like shake out the rest of the code to see what's leaving behind. It's a real fast way to identify code that's not connected. It may be legacy code that's just sitting there, or it could be a problem with the loader. But providing this visualization allows you to determine that extremely quickly. We have used this visual capability. It's so much easier to use than having to go and develop a whole series of queries in OrientDB to see the same thing. Now, a little bit more on that softball piece of code. In the Trilog malware, they had a whole group of things that are DLLs. You're looking at these different functions and these different libraries, and they have labels on them, but it's not connected to the rest of the code. This was our first attempt to run the Trisis malware through the @DISCO capabilities. And we determined at that point, yeah, we're all Linux people and everything we do in control systems is Unix-like based. So we kind of ignored Windows. Now we've retrained the model for Windows. When we see this view today, everything is connected. The next view is more of a 3D with a pin graphics that allows you to go back and forth to the different database areas so you can really drill down on the code. So this is exactly the same code, exactly the same view, but you'll see at the very bottom left-hand corner some query numbers showing up. You can click on those, you can go back and forth to the database, you can go and query specific subroutines, drill down, and actually see what the VEX codes are for that area. And then go back to highlight where it is in the visualization. There at the bottom, you're seeing some of those VEX commands. If you really need to understand what your code is doing for your most important safety instrumented systems, their life safety systems, this is a very interesting tool. As you're seeing here on that softball piece of code that's mainly DLLs, there's 84 different DLLs in that ball that are being used. And then the final view is our execution flow. We don't have a decent video for this one. It'll just be stills. But at the very top is the Trisis trilog.exec. And all those pink lines are showing all the calls for the different areas. The huge amount of calls in pieces on the bottom, these are the DLLs that we're seeing on the bottom that you can find out. And then you can drill down into them. This is a different view, not trilog, but this is a vulnerable library, a ubiquitous vulnerable library. And in that green box is that library and all the blocks it calls. When you just look at this function, you can see the patterns really quickly on the other two. These are versions, future versions of that same library. So future direction for these technologies, we're really fortunate. We have a lot of capabilities right now, a lot of different research happening. WiiBin right now is available on our GitHub. At Disco is available with additional protocols. And DiscoveryOverflow is in the process of being open sourced. We have a project called Firmware Command and Control, where we're going to go deeper into embedded systems and create a microkernel that can actually do cyber command and control inside that embedded system. We're going to take it a little bit out of static binaries and try to get more understanding of that symbolic execution side of it. So it's going to take these technologies and advance them and go forward. Same with deep learning malware. We're going to take the concepts of these and just point it towards malware, nothing but malware all the time. And our whole purpose for this is to kill those dumb static hashes that tell you what malware is. They are whack-a-mole, they are horrible to use, and we really want to move away from that and get to more context-rich, meaning here are the type of commands that we're seeing, here are the type of calls that they have to a context-rich indicator. And that's what I have. Is there any questions?
Somebody needs to let me unmute myself. So for those of you watching on the stream, you'll hear me, but I'm not able to unmute myself to talk to our speaker. So I'm trying to signal our Zoom leader.
Rita, I'm not seeing any questions in the track one. Awesome presentation.
Thank you, Sandra. We're really excited about these technologies. We're excited to get this forward. We're going to need a little bit of additional protocol with the at Disco application. The executive order that was signed in May about supply chain.
All right, so I have been allowed to unmute now. So we did get a question a little bit ago.
Oh, okay.
There was a question from Elvascu saying, would WiiBin be something that could be used on consumer IoT devices?
Absolutely. The whole kind of trick here is to make sure you're pulling the firmware off of those devices. There's many different techniques to do that. We developed one in-house, but there's others that are available to you that are open source. But definitely, we've used it on, again, we're focused mainly on the electric grid. So we've used this capability with relays, meters, weird little communication devices that do everything. But pulling that binary firmware is where you want to start. And then use WiiBin to figure out how to get it loaded into whatever you're using, whether it's just a bin walk or your own reverse engineering, or if you have access to other things such as at Disco to do that automatic reverse engineering and creating corpora.
That makes a lot of sense. So you do your standard, whatever your mechanism for pulling firmware off of your device, and then your system does allow use of that. So that's good to hear. There was a call out also. Somebody was commenting on Debrin Scombe saying, "Way to go, Katrina." So you called out your Karina. Oops, sorry.
Yeah, Karina.
You called out your intern program. We'd love to hear a little bit more about that in our last little bit of time.
Yes, this year, with COVID, I've only had interns for 3 years. And then last year I had 6 interns. One of them was Karina. She's going to be a senior in high school. They wouldn't let me hire her. What can I do? But out of the other ones, another one was only a sophomore. I hired 3 of the 4 that were graduating. This is how we actually find our talent. Very, very satisfied with being able to do that. This year with COVID, I was like, oh, how are we going to do this? How are we going to do this? With the help of Brian Beckman and the release of these tools, we were able to create some very interesting cyber challenges, making it very competitive for the different interns and keep up the interest. We had multiple meetings every week to keep them interested, to keep them engaged. They did some great work for us. They were able to test a lot of these applications. They were able to do a lot of analysis with us. So I was really happy. This year I had 11 official interns and then about another 5 that jumped on to do some of our activities because it's so strange. But yes, our intern are, definitely get to the INL site. If you have people in college, have them put in there. We start interviewing our interns February, March, get them lined up. It's been a really interesting role, and Zach Priest and Brian Beckman helped me so much with our interns. It was a great experience for us again this year.
Hey, check that out, Zach. You got a call out. Zach is actually on the chat listening right now. So excellent. Thank you so much for coming and presenting to us. In fact, for any of you who really enjoyed this one, Rita is going to be doing another talk in a few hours. Looks like 16:30. She will be presenting structured threat for shareable, actionable, and implementable. I'm sure I said that wrong. Intelligence. It is our pleasure to have you here. At the end of this talk, is there any one wrap-up takeaway you would like us to all pull forward?
This is the Idaho National Lab has so many people working in cybersecurity for critical infrastructure. This is a national need. We are able to find unbelievable talent local, bring other unbelievable talent in. I'm very proud of being a Idahoan and being able to have this type of unbelievably mind-bleeding technologies that we develop and move forward in research. I'm very happy that we're able to do this. I'm thrilled that I'm able to work with so many unbelievably smart people. It's been a really interesting it's supposed to be the end of my career, but I want to keep going because this research is so interesting.
Well, that's a seal of approval that not many organizations get. Well, thank you very much. If anybody has any additional questions for Rita, please feel free to drop them into the Track 1 chat, and we will hear more about all of this later.